Hello, everybody. Welcome to this third webinar in the SO-CHIC project's webinar series. Today we've got two presentations, but we also have a couple of extra speakers who will join in the discussion afterwards. We have Svein Østerhus and Shenjie Zhou, who will be speaking on the ocean variabilities in the Southern Weddell Sea with their two presentations. My name is Joseph Nolan from the European Polar Board. But before we start, just a little bit of housekeeping for the webinar. The webinar has been recorded, just so everybody knows, and the recording will be available afterwards on the SO-CHIC's YouTube channel. If you have any questions during the webinar for either of the presentations or in the discussion section, you can type those into the Q&A box at the bottom. You should have a button at the bottom of your screen somewhere where you can type your questions and we'll get to those. You can also, there should be a button somewhere if you can find it to virtually raise your hand, and that indicates you'd like to speak. So we can unmute you and then you can ask your question via audio if you would like. Generally, we will save the questions until the end after the presentations, but if there is a question that's very specific to something in one of the presentations, then we will we can go to that straight away. There is also the chat box is available there, so if anybody wants to add some extra information or link to papers and so on, that's always very welcome there. And I think that is all I've got to say at this stage, so I'm going to hand over to our first presentation, which is from Svein.
Thank you. I will try to share my screen. Okay, do you see my, oh, sorry, starting not with the beginning now. So I hope you see my screen okay now. So I will address this ocean variability with looking on from some of our long-term observatory observation from fixed station, or it means more instrumental station. And my name is Svein Østerhus, already told. I'm from a research company called Norwegian Research Center, and I'm living up in Bergen in Norway. So my thinking is that I will just shortly remind you about what SO-CHIC is about. And so I will try to set the Weddell Sea in a more global setting, but why we are so interested in study the Weddell Sea. And so I will go a little more into more local phenomena, what happened in the Southern Weddell Sea in the Fischner-Ronne ice shelf area. And so tell a little about, do we have anything to fear when coming to climate change? And so say something about what is the role of ice shelves in the climate system. Little about the dense water formation and the transformation of this dense water to an export to the deep ocean. And so I will then present you what we have of fixed point observing system and show you very few results. So about SO-CHIC, this is the only slides I will show directly about SO-CHIC. So the main objective there is addressing heat and carbon uptake in the Southern Ocean. What I will talk about is related, but I will not talk about but much better but carbon uptake, and so I will be more focused on current system and deep water formation in general. So to the Weddell Sea, and so the Weddell Sea and Antarctica, the process is related to the deep water formation there is the same processes as in the Arctic, but there's some really big difference. So that is, of course, the North Pole is covered by sea ice, the South Pole is covered by ice cap. But the other very important difference is that you have this big ice shelves in Antarctica, and you have many. In Arctic, you also have ice shelves, but very few and small compared to Antarctica. So, of that reason, the coldest water and the most dense water is formed in Antarctica, and this is sinking into the bottom of the world ocean, and is spreading out in all the world ocean. Now, in fact, in the Atlantic Ocean, it makes its way the whole way to Ireland, and this is, of course, is a part of this global thermal circulation or meridional overturning circulation. And as you can see from that one, the black part there, this is the bottom temperature around Antarctica, and the black is the coldest, and you can really see that that is coming here from the Southern Weddell Sea. So we will, for that reason, focus on this area. So the Southern Weddell Sea, you have this Fischner-Ronne ice shelf. This is, by the volume, the biggest ice shelf in the world ocean. The Ross ice shelf is the bigger coming to the area, and it's also surrounded or outside by a quite wide continental shelf. That is important coming to the process. So what do we observe in Antarctica? I'm sure we have heard about all this melting going on, and that is mainly in the Amundsen Sea, where the warm water is penetrating underneath the ice shelves. And for example, the Pan Island ice shelf that's melting rapidly. We have until recently believed that the biggest ice shelves, the Fischner-Ronne and the Ross ice shelf, is safe due to all the cold water sitting on the continental shelves outside outside ice shelves. And we also believe that the East Antarctica is relatively safe for ocean-induced melting due to the wind and current system. But maybe we can't take that as granted. But let us first see about what is the main theories or hypotheses we have. So one is just saying that, okay, due to this cold dense water sitting on the shelves, this warm water will not make it into the Fischner-Ronne and the Ross ice shelf. And we should be safe. Of course, Antarctica will melt gradually in any case due to the melting in the Amundsen Sea, but the big ice shelf, we at least have to quite recently believe that was safe for this for a dramatic change in the melt rate. But some new modeling results is indicating that we cannot take that as granted. I will show you the results later on, but it's indicating that some dramatic changes may appear in a few decades from now. So, to be able to talk about the process, we have to present what is the role of the Antarctic ice shelf in our climate. And there's two areas where the ice shelf play a very important role. And the first one is a very big heat exchanger. So that is the reason that it produced this densest and coldest water in the world ocean. So due to freezing and melting melting underneath the ice shelf on the high pressure, we produce very cold water and dense water that is spilling over the sill, continental, and is bringing down the continental slope and into the deep ocean and going into this world ocean circulation. The other important role is that it is to keep the ice cap in place. So it reduces the speed of the ice flowing out from the ice sheet covering the South Pole area. So we have two important roles to play there. And according to IPCC, the changes here in maybe one of the big question unknown, which we need to address if we want to really to predict, for example, make good estimate of sea level rise in the coming years or coming decades. So little about the process we're going on. So outside the Fishner-Ronne ice shelf, so this is Ronne and this is Fishner. Here during the winter time, you produce high saline, what we call high saline shelf water by forming ice. And when you form ice, you add salt to the water, and that's the reason getting we call it high salinity. This water is on the freezing point for seawater on surface, minus 1.9, and some of it circulating around underneath the Fishner-Ronne ice shelf, around the Bergen Island, and they're coming out again as a super cold water with temperature below the sea surface freezing point. And we call that the ice shelf water. So again, it's the same process here as up in the north with the formation of deep water due to cool down the water, freeze, and sea ice is formed, sea ice is transported away, and more sea ice can be formed, and more high salinity shelf water produced. And some of it is circulating on ice shelf, but some of course also leaving directly out. So this is just another way of looking at it. So here you have the sea ice form and the circulation underneath there, and then it's coming out, it's cold, dense, spilling over the edge of the continent and floating down the continental slope. And that is the surge of the coldest and densest water that is filling all the world ocean's bottom layer. But they also have this dense water also is not only forming not only producing the overflow and the deep water, it also forms dense and cold water that's sitting here on the wide shelf, and this is protecting the ice shelf from the warmer water, which you find outside the continental shelf. So this warm water is trying to penetrate into the ice shelf, and underneath the ice shelf, this dense water is knocking it back again. So that is quite important, coming to melt the ocean-induced melting of the ice shelf in Antarctica. So of course, to monitor changes in the system is important. So during over many decades now, we have tried to establish an observing system. Especially our British friends from Bath have been very active drilling holes to the ice shelves. I have been lucky to join in and so on. And for the recent years, Germany also have been contribute very strongly to this program. Outside the ice shelf, in the sea ice cover area, on the continental shelf. We have a long time series going back to 1977. This is the longest existing time series, but as we will see later, it's very gappy. And now we are trying to have more moorings beneath the sea ice to cover out the outflow and also a possible warm inflow. And today, we are, in addition to Germany, Norway, and Britain, we have also France. So SO-CHIC is in here with JB and his group. Yeah, so schematically, you can see like we have all these moorings out there underneath the sea ice, and we have drilled to the ice shelf and instrumented the cavity beneath the ice shelf. And of course, lucky enough that you have a surface where you can put some instrumentation, you can also send data back home. So I will, during my presentation, only show two time series. One is from beneath the Ronny ice shelf, on what we call side 5, and the other one is out at the shelf break, where there's dense water is spilling over the sill and then streaming down to the deep ocean. So this is a time series from beneath the Ronny ice shelf. The thickness here is, I think, is 775 meters. And we started that time series already in 1999. And you can see here in the beginning, right, so this is you have the years going on here. And this is simply the speed of the current. But you can interpret the speed as the production of high salinity shelf water, or if you want, the amount of heat which can melt the base of the ice shelf. So you see that was really high in the beginning. That had to do with a very special sea ice condition out in the Southern Weddell Sea on the Ronny shelf area, and in resulting in a high production of high salinity shelf water the winter after. So it was very little ice, but so when the winter came, it produced a huge amount of high salinity shelf water due to the open ocean, and you could produce a lot of ice. But this rapidly, only after a year, it dropped down to a more normal situation and have been stable for the coming years. But here you can see it's a big gap from 2002 to 2015. So we didn't manage to keep it running for this year because we have to drill new holes in it. But here we re-established the station, and since that it have been quite stable, but you see it's a little lower than it used to be. So we think if any changes have happened, we produce less high salinity shelf water today compared to 20 years ago. And that should mean less melting of on the base underneath the ice shelf. And that is also what Otto is observing. So here the red part here is the melting in the Amundsen Sea and the Pan Island and other ice shelves there. But you see here the blue color here is meaning that the here is getting thicker. So that is the situation over some years with changes in the ice thickness. So it seems that, okay, it looks like it's, we are on the safe side. No increase in the melt rate of the fictional run. So this also means that this force that keep the inland ice in place, the ice sheet in place, or reduce the speed of the ice sheet to float out, is still in place. No changes have been observed. But as I said, this also means, don't know about that, but if you produce less of this high salinity shelf water, you also produce less of this dense water that is protecting the ice shelf from this warm water. And this is one of the things we're clearing in. Maybe we can come to a tipping point there, but there's too little dense water is formed. And this force, this protection is going away, and this warm water can penetrate in. And this is what the model predict. So the model is predicting that due to changes in atmospheric driving forces and changes in sea ice situation production, will after some years allow this warm water to penetrate and make its way onto the continental shelf and in underneath the ice shelf. And that will have dramatic effect. What this specific model from Helmer et al. Is predicting is that the basal melt rate for the Fichner Ronna, which is on 20 centimeter per year today, will increase to 400 centimeter per year in 2060, only 40 years from now. This is quite dramatic. So this is one of the reasons that we really want to understand better what's going on and have in place a very good monitoring system, an early warning system, if you want. So if this happens, of course, the increased melt rate, you will this force that keep the ice cap or the ice sheet in place will be weaker, and more ice will flow out into the open ocean, and you will get sea level rise. So here is just a demonstration of one of the monitoring system we have. So this is again with side 5, 775 meter thick ice. We have drilled through it, instrument the layer between the base of the sea ice and the bottom with the instruments, but with current meters, temperature sensor, conductivity for salinity, pressure, and dissolved oxygen. And this system is sending data back once every hour. And as I earlier told, we started already in 1999. And this is just wholly data from the different depths. But again, you see there's a big gaps there, more gaps. But we hope now, or at least we try to keep this running continuous for hopefully 5 to 10 years more. So I just went in to the system today to check what's coming in. So it was 10 or 11 o'clock today, saying the temperature is minus 2.1. And this is just giving the pressure of so we know which depth the sensor is in. So it's working, and we think this is really important. And it's very good to have it in real time, even through this very slow TV. You have to wait some years before you see any changes, I assume. I hope so, at least. But to have it real time, we will be, if anything dramatic is changing, we can give an early warning or a warning of what's coming. So that is underneath the ice shelf. But we do also monitoring both the inflow here and also the overflow. So what do we see here? If we look into, we do have a relative long time series from this place, going back to 1977. But as you see, starting here in 1977. But so as many years gap, another year with gaps. So the time series is very gappy. We are now trying with a good cooperation and good logistic support from Germany and Britain, and a very nice team of people, scientists involved here. We try to make a more continuous time series. So when I'm after this season, I hope to be able to extend this time series So maybe we can be able to say something about trend, because with this gap time, so we cannot say anything about the trend. Oh, if it was a very huge trend, we could maybe have done it. So I cannot really tell if any changes been any changes in the overflow air. But in next presentation, you will see that Shenjie will present some other data from the Weddell Sea where we can say something about trends. So back to keeping this activity or observation system in place. This is a very demanding and a very expensive operation. So international cooperation is essential. We cannot do it with single teams from one country. So here we need all the logistics support we can get, and as I said, it's mainly the Germany and Britain who are providing the logistic support there. And today, I'm now sitting in quarantine in Bremerhaven, making ready for a cruise with Polarstar to maintain or servicing the moorings out there underneath the sea ice. But it's a Corona time, so this is the reason I'm in quarantine, preparing for it. So we even have to involve Lufthansa because we need a Corona-safe flight, and Lufthansa will bring us from Hamburg to the Falklands in a special Corona-safe flight there, and even the crew on the airplane had to sit there for 16 days in quarantine. So I think they will bring us, I'm sure they will bring us Corona safe to the ship. But this also just tells us how difficult it is to operate in a remote area in these days, because we cannot take the risk to bring any Corona on the ship. That will, of course, destroy the whole thing, and we have to return again without manage to get this important, for us, and very important survey and service of the instrumentation in the Southern Weddell Sea. Okay, that was what I wanted to present for you. So thank you.
Thank you very much, Svein. I can't see any questions that have come through yet, so I think we'll just continue straight on to the next presentation, and we'll get some questions later on. So the next speaker is Shinji from the British Antarctic Survey. So over to you.
Right, thanks, Joseph. I will just share my screen. Is the screen showing just fine?
Yep, all looks good.
Great. Okay, so hi everyone. My name is Shinji. I'm a postdoc at British Antarctic Survey, and I'm working with Svein, Andrew, and Casimir and other colleagues on the work package 3 of the SO-CHIC project. So, well, Svein has given us a little bit introduction about the importance of the Southern Ocean and the objective of the SO-CHIC project, but I thought it would be good to stress on that. So here is 2 nice figures from McMurdy's 2019 paper showing that how the Southern Ocean area is a key region of connecting the world's ocean, and how little data that we actually have down south in the Southern Ocean, and especially in this wide area in the Weddell Sea. So the reason that we are looking at the Southern Ocean is basically that this is an area where the world ocean waters connect each other and interact each other. The deep water from the water ocean, it's upwelled in the Southern Ocean and make contact with the atmosphere and the cryosphere. Part of this water, it gets warmed and freshened at the surface and transported northward and subducted into the ocean interior. And the remainder of these waters is converted into a very dense water through the cooling and brine rejection with the contact of the very cool air and also the ice. So this water will flow back into the abyss of the ocean. And through these interactions among the ocean and atmosphere and cryosphere, the Southern Ocean also takes up the disproportionately large amount of the heat and the carbon from the atmosphere and carries them back into the ocean via these pathways to keep our planet habitable. So, but as important as it is, the Southern Ocean to the climate, it is also known as the data desert, where basically there's very limited amount of the direct observation are available, mainly due to the severe sea states, rapidly evolving weather systems, and also the extensive sea ice coverage, especially during the winter period, which contributes to a very large uncertainty in the estimates of some of the key climate variables, such as the air-sea heat and carbon fluxes, and also the pathways of water mass connection between the Southern Ocean and the rest of the world. So the SO-CHIC project is the overall objective is trying to quantify the variability of the Southern Ocean heat and carbon budget by looking at different key processes as presented here and their feedbacks to the climate systems across different work packages by means of direct observation and the numerical models. Also, these will be supported by the data management through work package 7 and the dissemination of the information through work package 8 in the European Polar Board. So what we do in the work package 3 is focusing on the deep ventilation pathways, aka the formation of the dense water at the western and the southwestern Weddell Sea ice shelf, as Svein just mentioned. So there is 4 tasks that constitute the work package 3. So task 3.1 is focused on the fixed point mooring observation near the dense water formation sites. And Svein has just nicely illustrated that the task 3.1 will assemble a time series from the past and will extend these time series in the future field campaigns. The task 3.2 is focused on the slope processes that links the upstream formation and the downstream export of the Weddell Sea deep water. So task 3.3 is mainly the modeling effort that is aiming to map the bottom water export pathway and quantifying the dense water consumption via various processes that mix these dense water with surrounding water masses while it travels along the streamline. And the task 3.4, which is what I'm going to talk a little bit about here, is basically it's trying to combining all the mooring time series along the ice shelves that are maintained by our partners to establish a direct observational evidence of the long-term variability of the dense water formation. And in parallel to that, we're going to summarize the existing hydrographic data in the Weddell Sea to provide a more broader spatial scale context to the mooring time series. And hopefully we can try to fill some of the gaps in the mooring time series that we see in Svein's slides. The hydrographic data sets are also going to help us to understand the role played by different gyre dynamics in circulating and exporting dense water with a combination of the newly available sea ice corrected sea surface height measurements. And ultimately, we want to build up a dynamical framework to be able to explain the observed water mass properties with a connection to the external forcing, such as the changes in the wind, buoyancy fluxes, and the sea ice extents. So where are we now at the moment? So where we have gathered the existing hydrographic measurements in the Weddell Sea. So these hydrographic data are collected by the ship-based CDD casts, the Argo floats, and the seaborne profilers. All these three platforms are essentially taking measurements of temperature and salinity in function of the profile through the water column via the instruments called CTD profilers. So we did some brief overview of this collection of data sets, but we haven't really dug into it for any possibility of, excuse me, any possibility of forging a long time series of water mass property out of yet. But we did have take a closer look at the ship-based CDD transects along the world ocean circulation experiment sections that goes across the Weddell Sea area. And because these sections has been regularly repeated by the cruises over the past 20+ years, so we'll be able to have a general idea of the long-term trend and variability of the Weddell Sea dense water. And this trend is going to be compared to the gyre intensity indices derived from the sea ice corrected sea surface height products, which actually gives us some suggestive investigation for the next few months. So here, just a quick overview of all the available hydrographic data sets within the Weddell Sea and also in the surrounding seas. So you can see at the top left is at the top right is the area of all these hydrographic data sets being distributed. So zonally it extends all the way from 75 degree west to the 35 degree east, and meridionally it extends all the way to the 50 degree south. So in total, we are able to identify over 10,000 CDD profiles, about 40,000 Argo floats and SO-CHIC floats, and more than 100,000 seaborne profilers since the 1970s. And actually, the inclusion of the floats and the seals since early 2000s has substantially increased the sampling frequency and the spatial coverage of the available observational data in the Weddell Sea. And the float and the seal also, they complement the seasonal biased ship-based CDD casts, because during the winter time, it is really inaccessible for the ship to go to that south in the Weddell Sea, but seals and floats can go there. And last but not least, the seals has also largely improved the visibility extent of the hydrographic state of the Weddell Sea by sampling more southern Weddell Sea waters near the ice shelf area. So the hydrographic data set, as we see in the last slides, has actually demonstrated a very good seasonal coverage. So if you look at the animation at the top, it shows the distribution of the data set in function of the months assembled over the whole observing period since the 1970s. But meanwhile, it undergoes very large interannual variation in terms of the spatial distribution of the available measurements and also number of the observations. So this means that this collection of the data tends to make a better representation of the Weddell Sea seasonal climatology rather than the long-term variability. Also, this data set can be a very valuable asset for the ocean state estimate. And we are currently working partially with our colleague at British Antarctic Survey, Dan Jones, with a project on developing a Weddell Sea ocean ice shelf estimate using this hydrographic data set as a observational constraints to the model. With the Argo float being the most widely distributed platforms in the Weddell Sea, it also leads to a undersampled deep ocean, deeper than 2000, because the Argo floats does not really travel that deep. So here in the middle, the animation is showing the calculated density, neutral density surface depths of the Weddell Sea deep water, and we can see the data point is really sparse across the time. And most of these observation is coming from either the sears or the ship-based CDD casts. But in the meantime, the collection of these data sets can actually make a fairly good estimate over along the coast area, as we see here in the last figure here. In this paper, the Push et al. 2020, the author has succeeded to interpolate all the hydrographic data sets along the cross slope sections along the Southern Weddell Sea, and they are able to see some emerging evidence of the correlation of the water masses anomalies and the wind-driven boundary currents at the seasonal timescales. And so in the future, we are also trying to looking at any feasibility of objective mapping schemes to make the most use of this collection of the hydrographic data sets. But on the other hand, there have been a regular ship-based CDD casts along several hydrographic sections, as we mentioned, that rides over the Weddell Sea over the past 20 plus years. So these schematics here shows that there are 3 hydrographic sections are taking measurements within the Weddell Gyre directly and also across its boundary. So the A12 section and SR4 section nicely go across the Weddell Gyre at its eastern boundary and also across the center of the gyre. And the A23, it rides at the eastern end of the southern Scotia Ridge next to the Orkney Passage, which is one of the main pathways, which is believed to via which the dense water communicates between the Weddell Sea and the Scotia Sea. And it is also noted that this strong bathymetry feature of the southern Scotia Ridge at the northern boundary, it blocks the dense isopycnals accessible to the Scotia Sea. So any changes of the isopycnal depths within the gyre can be manifested in the density surface of the dense water that exported through the northern boundary, which we are going to see in the next 2 slides. So here we plotted the time series of the depths of nutrient density surfaces at 3 transects that stands for the upper and the lower density bounds of the warm deep water, the upper Weddell Sea deep water, the lower Weddell Sea deep water, and the Weddell Sea bottom water that distributed in the Weddell Sea. So as we can see that we have observed that over the past 20 plus years, all the hydrographic data section has detected a statistically significant deepening of the nutrient density surfaces. This deepening of the dense water isopycnals have important implications on the dense water that exported to the Scotia Sea and sequestering transformation into the Antarctic bottom water through the northern boundary. This is confirmed by Paul Abrahamson and his colleagues in a 2019 paper that the changes in the lower Weddell Sea deep water observed in the Scotia Sea, actually it follows quite well with the Weddell Sea bottom water density surface that observed in the Weddell Sea along the A23 sections. So here we also calculate the volume change of the observed water masses in form of the normalized layer thickness between the characteristic nutrient density surfaces, as we see in the last slides. It is noted that there is a statistically significant increase of the warm deep water volume at the section 812. It seems to suggest that there is increased inflow of the CDW into the basin, and at all 3 sections, we all find a statistically significant decrease of the Weddell Sea bottom water volume. So I think to be able to reconcile this reduction of the Weddell Sea bottom water detected at all three sections, we will need to look at the combination of the long time series near the ice shelves, and also the collection of the hydrographic data that we mentioned that near the ice shelves, to be able to understand this long-term decrease of the Weddell Sea bottom water. And there's also have been emerging evidence showing that there's a increased warm deep water confirmed by a study came out just last year, Strauss et al. 2020. They showing that there's a multi-decadal warming of the deep Weddell Sea along the A12 transect and also SR4 transect, and this warming trend is statistically significant, and also the warming trend has been coinciding with the deepening of isopycnals that we observed across these transects. Also, with addition of the information from A2023, we can see that the warming trend with this statistic significance spills over the SSR, the Southern Scotia Ridge, at this section. This actually highlights the correlation between the Weddell Sea deep water that are being observed in the Scotia Sea and the deep and bottom water that is stored in the Weddell Sea. What is also shown in this study is that it seems that there is an increased, there is a correlation between this increased advected deep warm water, and the spin up of the gyro circulation. So with the aid of the newly available ice-corrected sea surface height products, we'll be able to confirm this mechanism by compare the sea surface height derived gyro intensity directly to the observed trend of the hydrograph data section. So here's the just a quick overview of the time series that we derived from the time series of the gyro-related indices that we derived from the sea surface height products. So the sea surface height data that we used here is ice-corrected data, and it's a combination of two satellite missions. So it's a 12-year ENVISAT and a 11-year cryosat measurement, with the overlapping period between the two missions from 2010 to 2012. So all the along track data has been graded and smoothed and binned into the monthly interval. And we eliminate the intersatellite offset using the area average mean difference map. And we also correct the stripe pattern induced by cryosat orbit cycle by using the ERF reconstruction method. So the gyro edge is identified as the largest closed contour of the monthly dynamic topography map. So from the top to bottom, what I show here is the monthly time series and the long-term trend of the gyro area, the estimated barotropic transport from the sea surface height derived geostrophic velocity, and also the gyro means sea level anomaly, and also the sea level anomaly difference between the center of the gyre and the edge of the gyre. And at the right, I'm showing the seasonal cycle of those corresponding variables. And there's a distinct seasonal cycle of the Weddell gyre as we expected. So basically the Weddell gyre, it expands during the winter time, accompanied with slightly intensified barotropic transport and lower sea level anomaly, and enlarged sea level anomaly difference between the center and the edge. However, if we took a look at the long-term trend of the gyro intensity, we actually have observed a slow declining of the gyro intensity characterized by the decrease of the barotropic transport. Although there's the statistical significance is low, but there's certainly no clear sign of spin up of the gyre over the past 20 years. So to summarize what what we have at the moment with all these observation data is that we found a multi-decadal deepening of the SO-CHIC nodes that have been detected along these transactions. But there's a contrast volume changes between the Weddell Sea deep water and the Weddell Sea bottom water, characterized by the statistic significant reduction of the Weddell Sea bottom water volume. There's also a multi-decadal warming being reported in the past studies, which has been attributed to the increased advection of warm deep water and associated with the baroclinic spin up of the gyre. But by looking at the hydrographic data sets and an uplifting of the sea surface height, it seems to suggest that there is a rather horizontally uniform deepening of the SO-CHIC node due to the reduction of the Weddell Sea bottom water volume. Whether it can be attributed to the gyre intensity changes or associated dense water formation, well, it needs further investigation on the gyre structure and the hydrographic data near the ice shelves, which is going to be what we are going to do for the next few months. And thank you.
Thank you very much, Shenjie. That was a very thorough presentation. So we now have a little bit of time for questions and discussion for our two presenters, but also Andrew and Casimir are on the line as well to join in. So if you have any questions, you can type those into the question and answer box, or you can use the raise hand button to indicate you'd like to speak yourself, and we can unmute you. I don't see any questions just yet, but I'm sure some will come through. But maybe to start, I was thinking, well, how is the are the bottom water processes in the Weddell Sea, are they influenced particularly by the bathymetry of the continental shelf? And might this change if the grounding line were to retreat, if it ever did? Or is that something that's considered? I don't know.
That's for you, Andrew.
Well, I'm maybe not the best person to comment on the actual processes underneath the ice shelf and how that's affected by the grounding line. I think that would be Sven. But in terms of the wider role of bathymetry, it absolutely is critical in its circulation. First in its export off the shelf. So there's sort of the process of forming this dense shelf water and ice shelf water underneath the ice shelves. And then that has to be exported from the relatively shallow continental shelves where it's formed into the deep interior, ocean interior. And there's various, and this is usually done as the water is much denser than all the surrounding waters. As it moves off the slope, it sort of cascades down the slope, down to the abyss. However, this is a very turbulent process, and as it goes down, it entrains lots of the ambient water mass. And there's various discussions about the relative importance of things like subterranean canyons in actually sort of shielding this really dense water mass from all that entrainment. So there's the actual pathways of this dense water off the shelf into the ocean interior is really important, and bathymetry plays a big role there. And once it's actually down in the interior, then its circulation within the Weddell Sea is very much constrained by the boundaries of the Weddell Sea. So as Shenji was alluding to, the exit pathways are through the South Scotia Ridge, and it's on the northern side of the Weddell Sea, and that has various little sills and passages. And if the isopycnals, so this very densest layer, is getting successively deeper, fewer and fewer of these relatively shallow passages through the wall of mountains are available to the water, and so that will really dictate where the densest water masses can actually escape, whether or not they go into the Scotia Sea, or if they have to keep following the South Scotia Ridge all the way around to the east before they finally get ejected sort of towards the Indian sector. So yeah, the bathymetry is really important.
Great. Anybody else want to add to that? We've got a couple of questions that are starting to come through. I think we'll maybe unless somebody has an answer further to add to Andrew on that. I think we'll go on to the first question from Dale. A question for Svein. I was wondering what kind of sea ice phenomenon that slowed down the Filchner-Ronne shelf speeds in the late 70s. What were the sea ice phenomenon that slowed them down, slowed down the ice shelf? And is that something we have enough knowledge about? And is it a recurring phenomenon that might happen again?
Yeah, I think this, he or she probably meant in the late 90s. So we don't have much information about, let's say. So it's big. Well, it must have to do with the wind system, but certainly this year or this summer, in 1998, most of the sea ice over the continental shelf outside Ronne ice shelf was gone. If it was a very anomaly situation that brought sea ice out, or this is something that periodically happened, we don't know. But we have only seen that once. Normally, we cannot sail in this area at all, but this year it was completely, not completely open, but easy to sail into it. So when you started out after a summer with no ice in the area, and you get this, when the winter starting, you have a huge area to freeze ice in, and so you produce a lot of high saline shield. If that is but after this, it not happened since, so it's more than 20 years since it happened. And normally, so what we have experienced the last 20 years is more or less that it's being more and more sea ice cover in the area, and more and more difficult to operate the ship. So we are really fighting hard, even with a strong research vessel as Polarstern, to make it through the sea ice there, even in the best part of the summer. So I don't know if we are looking into, of course, we do see changes, for example, in the southern annual mode, in the wind system, that may make changes in the sea ice production. But this was a very special year, this 1998.
Great. We have another question from JB, coordinator of SO-CHIC. So important question, of course, towards Shenjie. There are quite a few studies that have documented decadal variability in bottom water characteristics and transport. Do you see any hints of such variability at the repeated sections, or only consistent long-term trends? And thank you for the great talk.
Well, maybe that's because I didn't really read through all the literature just yet, but in regard of these question, I haven't came across a clear message to explaining the reduction of the bottom water volume. And I think in Paul's paper, the Paul Abrahamson 2019, yeah, they certainly found the same trend of this bottom water volume reduction, but I think they stated clearly that there's no existing long-term time series available at the moment to robustly monitoring the dense water at the dense water formation site. So I think one of the of our future plan is trying to extract some information from the collection of that hydrographic data sets from various platforms, and to hopefully can forge a long time series near the ice shelves region, and combine those signals with what Svein has near the ice shelf to be able to get some sense of how the bottom water volume variability and the trends are from.
Okay, great. I think that yeah, answered the question very well. Thanks. If there's, I can't see more questions just coming through quite at the moment, but we've got maybe just a couple more minutes before we can close. I was going to ask how affected could potentially, well, already been affected, but how much would the planned work in SO-CHIC, particularly in this work package, be impacted if the ship-based surveys were not possible? How much of the work could be carried out with the existing moorings and other sources of observations that are available?
I can address that. Well, the existing mooring, the mooring we will recover and redeploy this season. Some was deployed 5 years ago, another 3 years ago. So we are coming to the end of our lifetime. So we need to have a ship in place this season, or at least next season, to be able to recover the moorings and redeploy to continue the time series. Normally, this kind of moorings that we are deploying underneath the sea ice, the maximum we could think about is 5-6 years in operation before we have to replace. But that is also my thinking, that we have to improve our system through the technology to build an observing system that we can deploy and that will last for 10+ years. This is the case for some of the systems we have on the ice shelf. So they can, in the principle, run forever if you have power supply on the surface. But you have to go back there, maybe not yearly, but you could got too many years between, because we have the snow falling down and it's building up. So you have to dig down and lift the instrument boxes and lift the antenna to be able to receive the data. And of course, the solar panel and the battery package need to be replaced and have some service at least. So we strongly depend on. So this is very important for us to have this polar stern expedition this season. That is also the reason that AVI, Alfred Wegener Institute, putting so much effort into have this going in this really difficult situation with the corona. Having to charge a big airplane from Lufthansa and having Lufthansa to set up a huge operation for us just to make it to Polarstern at the Falklands is a demanding, very difficult, and of course very expensive operation.
Great, thank you.
If I could add to that, so that's the moorings component of this work package, but the other components, so that led by Shenjie and Casimir and the AVI component, these are all reliant on existing data and model efforts, so none of it actually depends. I mean, obviously more data as it comes in will be assimilated and it's nice, but none of it actually depends on getting new data in.
Good. So within the coming months or so, there will be more results, regardless of the cruises.
I have to say, Shenji's done a magnificent job. He's only been working since last July, and he's done a great job assimilating all the various disparate data sets that are out there.
I think it's a similar story for several of the work packages, and so SO-CHIC are trying to do as much as possible without the cruises, but some are able to make more progress than others. Okay, so I think we're more or less out of time. I can't see any further questions, so I think we will now wrap up a little bit. So this webinar has been recorded, so it will be available in the coming days on the SO-CHIC YouTube channel, so it can be rewatched and you can relive every moment. But also to share that with anybody who wasn't able to attend while we were live today. And I'm sure if you have any further questions, you can get in touch with our speakers and panelists. I'm sure you can find their contact details through the SO-CHIC website or elsewhere. We will be having another SO-CHIC webinar in the coming few weeks or so. That's yet to be determined, but keep an eye out for that. And yes, thank you everybody for attending, and thank you very, very much for our speakers and panelists, and I hope everybody enjoyed it.
Thank you for listening.
Thank you for listening.
Okay, thanks everybody, bye-bye.